Okay, in section 4 of topic 4, we're going to have a look at basic arithmetic operations to functions, which means we can apply addition, subtraction, multiplication, and division to any two of the functions.
Yeah.
This is similar to the concept for numbers. So let's see an example here. Very simple concept. Can you determine an equation for the function hx, which is obtained by adding fx and gx in each case? Then graph hx and state domain and range of each function. Okay, I'll give you 2 minutes to have a look at this example, and after that we'll have a look at solution together. Okay?
Okay.
Yeah, because you have my notes in at once, right? So from now on, I think you can print it out, and just write on that notes. That'll make it quicker, right?
Oh, okay.
And you can try to solve this question on that notes as well. Okay, let me know if you finish.
Okay. I'm not 100% sure how to do this.
Okay, no problem. Let's have a look at that. So hx equals fx plus gx. We simply add the expressions of gx and fx. So for question A, hx, we simply substitute the expression for fx and gx there. That's it. So what is fx? Fx is x squared, right? So substitute the symbol of fx with the expression of fx. Fx is simply x squared. So what is gx here? Gx is 3, so that simply adds 3, right? That is the expression of hx. You get it? So what is this domain? And we have already learned this type of function. This is a quadratic function, right? So if you have already learned that, it's very easy to evaluate its domain and range. What is this domain? There's no restriction. So the domain is simply the real number set R, right?
Yeah.
Or rigorously speaking, you should specify the domain like this. A set of numbers, each number is belonging to the real number set. Or you can simply state the domain is the whole real number set R. So what is this range? Usually you can sketch this graph to help you find its range. So this is a graph of x squared, right? So x squared plus 3 is simply translate the original function x squared up by 3 units. So this point here as y coordinate 3. So we know the range is from 3 all the way to positive infinity, right? You could specify it like this: y is greater than or equal to 3, and y belongs to the real number set. Or you could also simply say the range is from 3 to positive infinity. Use square bracket to indicate 3 is inclusive. Okay? Did you get it?
Yeah.
Okay, so how about b? And now you should be able to do b, right? hx equals fx plus gx. So what's fx in this case? Fx is x squared. What is gx? Gx is x, right? So that's the expression of hx. Again, this is simply a quadratic function. What is its domain? There's no restriction for the input x, so the domain is also real number set R, right? You get it?
Yeah.
And we know that this function is opening up, and because it can be factorized to x times x plus 1, there are two different zeros. One is here, one is here. So in order to evaluate its range, usually we'll find its lowest point, the y-coordinate of the lowest point here, right? We don't care about this x-coordinate, so we'll just leave it there, doesn't matter. The y-coordinate of that curve is, can you recall the formula? 4ac minus b squared, right? That's the y-coordinate of the vertex here. So what is a in this case? That's simply 4, right? A is 1, 4a is 4. 4ac is 0, right? Minus b squared. In this case, b is 1, so that is negative 1 over 4. Can you see that?
Yeah. Yeah.
Okay, let me check. Is it correct? So one of the 0 is negative 1. The other 0 is 0. So the x-coordinate is negative 1 over 2. If you insert that into the expression, you will end up with negative 1 over 4. So that is correct, right? Okay, so the range is simply from negative 1 over 4 to positive infinity, right? Did you get it? So that's why when you learn a new type function, you should be able to analyze its behavior by looking at its graph. The graph is a useful tool to help you analyze its behavior. All right. So make yourself familiar with the graph of different types of functions. Okay.
Okay.
All right. Let's see another example here. So note that we can do addition and subtraction with functions. We can also do multiplication and division on functions. So suppose fx equals x plus 3, gx equals x squared plus 8x plus 5. Can you determine an equation for each combined function below, and then state the domain of each combined function? Again, I'll give you some time to have a look at that, and let me know if you finish, okay?
Okay, I think I'm done.
All right. So first one.
You
Again,
times them.
yeah, we can just substitute the expression of x and gx there, right? So y equals x plus 3 times gx. Gx is x squared plus 8x, then plus 15. So we can expand it, or actually you can just leave it there. Doesn't matter if it's in an expanded form or affected form, right?
Yeah.
Because the question does not ask you to expand it, so we can just leave it there. What about the domain? Question does not ask you to find the range, but only the domain, right? Are there
Okay.
any restrictions? There's no restriction, so the domain is simply the whole real number set. That's the domain, right? So how about the second one? Y equals fx, which is x plus 3, divided by gx, which is x squared plus 8x plus 15. Okay, now can you factorize it? We can factorize the denominator as x plus 3, then x plus 5, right?
Yeah.
Okay, the question is, can you cancel x plus 3?
No. Actually, yeah, no.
No, because if you cancel that, you will end up like 1 over x plus 5, right?
Yeah.
These two functions are actually different. Why? Because in the second function, x can be negative 3, right? But in the first expression, x cannot be negative 3 because you have an x plus 3 here. So you lost a restriction for x in the second expression here, right? So do not simply cancel that.
Okay.
You can only cancel that after you specify the extra restriction. So for example, that equals, if you want to cancel that, you have to explicitly state x is not negative 3. After you specify this, then you can safely cancel x plus 3. You see that?
Yeah.
Okay, so in this case, this is the expression of the new function. So what is its domain? Which means, what is the restriction on x? The domain is x belongs to the real number set, but x cannot be negative 5, and x cannot be negative 3, right? X can be any real number except negative 5 and negative 3.
Okay.
Okay, do you have any questions?
No.
Alright, next let's have a look at the fifth operation we can apply on a function, which is called function composition. Okay, I'll explain this concept a little bit. So probably you haven't heard of that. This is different with the previous 4 operations. These 4 are called arithmetic operations, and the fifth is called composition. Composition function is a function that depends on another function. It is formed when one function is substituted into another, or in other words, we use one function as the input of the other function. For example, f of gx is a composite function that is formed when gx is substituted for x in fx, or we use gx as the input of fx, and it's read as f of g of x.
Yeah.
Okay, are you clear?
Well, let me just write that down.
Alright, so if I write it as g of f of x, they are different, okay? So this means we use fx as the input of gx. Can you see that? Can you see the difference? So note that the order of the function is important. As read from left to right, the second function is substituted into the first function. Another way we can use to express the composite function is this symbol here. You use a small circle to denote the word of. This means f of g of x, okay? Which is the alternative notation. That means the same as f of g of x. You see that?
Yeah.
Okay, by the way, there are some other notations for addition, subtraction, multiplication, and division. I forgot to mention that. So for example, for addition, fx plus gx is to simply add the expressions of the two functions, right? Sometimes we also use this notation, f plus g of x. You get it?
Yeah.
So x is the input and the expression is f plus g. And similarly, fx minus gx can also be written as f minus g of x. So this is the name of that function. This is the input of that function. And again, similarly, fx times gx can also be expressed as f times g of x. Solid dot here, not a circle, okay? And fx divided by gx, or fx over gx, can be expressed as f over g of x. Okay?
Yeah.
And so here, similarly, f of g of x can be expressed as f of g. This is the name of the new function of x. They are the same thing, okay?
Yeah.
Okay, let me give you an example. Suppose fx is a very simple function, x plus 1, and gx is also a very simple quadratic function, x squared. So in this case, what is f of g of x? Or sometimes expressed as f of g of x. So what is that?
Multiplication.
So you simply use gx as the input of fx, right? This is called composition. So gx is x squared. You simply use x squared as the input of fx. Can you see that?
Yeah.
So this composite function is actually x squared plus 1. So now I'll give you a quick quiz. So what is g of f of x? If you change the order, you might end up with different expressions, right? What is g of f of x?
X squared minus 1.
And you simply use fx as the input of gx, right? If you can't see that at a first glance, I suggest you to do this. So insert fx into the expression of gx will give you f. So when input is x, your output is x squared, right? So when the input is fx, the output will be fx squared. Can you see that? Just write one more step. So what is fx now? Fx is x plus 1. So that's simply x plus 1 squared, right? You get it? Any questions? And again, similarly for the previous question, if you can't see that at a first glance, then I suggest you do this. f of g of x, we simply use gx as the input of fx, right? So if you observe the expression of fx, when the input is x, the output is x plus 1. So if the input is gx, the output is gx plus 1, right? Just write one more step here. And next, what is gx? Gx is x squared. So eventually you will have the final expression, x squared plus 1, right? You see that? Any questions?
Oh, sorry, I didn't realize I was muted. No, I don't have any questions.
Okay. So let's try to solve this example here. Suppose if I give you two functions, fx equals x squared, gx equals x plus 3. Can you determine an equation for each composite function and give its domain? So I'll give you some time to complete this and let me know if you finish, okay?
Do I just write it down when I'm done, or?
Yes, you can write it on the screen.
Is this right for the first one? I'm not too sure.
Okay, in the first one, what is the input? The input is gx, right? If you're not sure, just try to insert gx here. So what will you get? If the input is x, output is x squared, right? So if the input is gx, the output should be gx squared. Can you see that?
Yeah.
So that's simply, what is gx here? Gx is x plus 3. So you simply have x plus 3 squared. Can you see that?
Oh, yeah, okay, yeah.
Yes, just treat gx as the input of fx. That's the meaning of f of gx. Okay, and now you can try the second and third. There is no multiplication, so we don't have this term here, this factor here.
So the second one is x plus 3 times x plus 3. Like this.
Second one, okay, note that it's close, but is not accurate. So in the second one, the input is fx, right?
Yeah.
So, okay, let's erase this first. So if fx is the input of gx, that means you need to insert fx here in gx here. Substitute the x in gx with fx, right? So that is fx plus 3. Because when the input is x, the output is x plus 3, right? Then when the input is fx, of course, the output is fx plus 3, right? You see that? So what is fx? Fx is x squared. Therefore, g of fx is x squared plus 3. You see that?
Yeah.
So how about f of fx? I'll give you a hint. So basically, you need to use fx as an input for fx. So that means you need to substitute the input of fx with fx itself. So use fx as input, insert it here, right?
Does that one equal?
Okay, I'll give you a metaphor. So how about, so if you know fx equals x squared, right? What about fu? What is fu? If fx equals x squared,
Becomes x squared.
then fu is actually u squared, right?
Oh yeah.
Yeah.
Oh, so f.
Yeah.
So
So wait a second. So how about f a little triangle?
Triangle squared.
Yeah, triangle square. So anything squared, right? So now the input is simply fx. So what is f of fx? You can treat fx as something like a triangle or u or m. Doesn't matter, right? As long as the input is fx, then you will always have the input squared. Can you see that?
Yeah.
So f of x is fx squared. So what is fx? You know the expression of fx, right?
Yeah.
And that's actually x squared, then squared, simplified to x to the power 4. You see that?
Yeah.
Okay, so can you try the next one? Follow the same concept. So this is called function composition. Basically, use a function as an input of another function.
Yeah.
Doesn't matter what the input is. For example, you could also say f of, so if you know fx equals x squared, so in this case we have gx, right? So if gx is x plus 3, if the input is x, output is x plus 3, and for example you want to evaluate something, then the output is always something plus 3, right? Doesn't matter what is your input here. It will always return a input plus 3. That's the meaning of function, right? So what is g of gx? The input is gx now, right?
X plus 3 squared. Well, x plus 3 times x plus 3.
No, you should write it one more step. Okay, let me restate this. Let's write it here. Okay, gx is x plus 3. This means we map an input x to an output x plus 3, right? X is simply a symbol. We could also say gm equals the input m plus 3. Can you see that? Doesn't matter what symbol you use here. If the input is something, the output is always the input plus 3. Can you see that? Or for example, g, let's say a star will give you a star plus 3, right? Or g, a small face is the small face plus 3, right? Can you see that?
Yeah.
So now you are only trying to evaluate g of gx.
So it
should
x plus 3 times x plus 3 plus 3.
Yes, it should be gx plus 3, right?
Yeah.
So what is gx plus 3? What is gx? Gx is x plus 3.
X.
So simply that is x plus 3 plus another 3, which is simplified to x plus 6, right? Right, clear?
Yeah.
Okay, so the last one is a little tricky. I'll explain this a little bit. So g inverse of gx, right? So naturally, you probably want to solve the expression of g inverse, right?
Yeah.
But remember, we have learned the property of the inverse of a function. F inverse of x is always x itself, or f inverse of fx is also x. Why this is true? Because, for example, we have two sets. This is your domain of fx, this is your range of fx. Under the effect of f, it maps any input here to a output here, right?
Yeah.
So in this way, we have f of x should equal y, and the inverse relation is labeled as f inverse, right? So here we have f inverse of y should equal x. Can you see that?
Yeah.
So what is y? Y is fx. Therefore, we have f inverse of fx is always x itself. Can you see that?
Yeah.
So we have proved this is actually true. For the first one, it's also, we can use the same method to prove this is also true. F inverse of fx. F of f inverse of x is x itself. Because it's simply a mapping along this direction and then mapped back. So it should be the input itself. This is an important property of inverse function. So that's simply x itself. Can you see that?
Yeah.
Okay, just make sure you know how to solve a composite function, okay?
Okay.
Alright, let's see another practice here. So if we let ux equals x squared plus 3x plus 2, and wx equals 1 over x minus 1, can you evaluate u of w of 2? And then evaluate w of u of negative 3.
The first one is 5 equals 5.
Why?
Because you first do W2, which is 1 over 1, and then you insert it into U.
Yeah, so first we can evaluate W2, right?
Yeah.
Okay, so, okay, let's say, what is W2? W2 is 1 over 2 minus 1, which is 1, right? Can you follow me?
Yeah.
And then U of W2 is actually U1, right? So what is U1? U1 is 1 squared plus 3 times 1 plus 2, which is 6, not 5, right?
Yeah.
Okay. Any other method?
I just used method 1.
Yeah. Method 1 is actually simplest. You simply evaluate the inner part and then the outer part, right? And also a generic method is, if you know the expression of Wx, then we can first evaluate U of Wx. If you know the expression of this function, just simply insert input to it, then you will get the image of that new function, right? So what is U of Wx? We simply use Wx as the input of U, right?
Yeah.
So that is Wx squared plus 3 times Wx, then plus 2. And then insert the expression of Wx there. So that's 1 over x minus 1 squared plus 3 over x minus 1, then plus 2. So this is the expression of U of W of x, right? So if you want to evaluate U of W of 2, then simply insert 2 into that expression. That'll give you 1 over 2 minus 1 squared plus 3 over 2 minus 1, then plus 3. That'll give you 1 plus 3 plus 2, which is 6. You see that?
Yeah.
Okay, now can you use the two different methods to evaluate W of U of negative 3?
That's equals 1.
Yes, first method is to evaluate U negative 3 first, right? So U negative 3 is negative 3 squared plus 3 by negative 3 plus 2. That'll give you 9 minus 9 plus 2. And then we evaluate W of U of negative 3, which is actually W of 2. W of 2 is 1 over 2 minus 1, which will give you 1, right? Of course, in the second method, you can also evaluate W of U of x first, right? So in this method, we use Ux as the input of Wx. Can you see that?
Yeah.
So that's 1 over Ux minus 1, right? And then insert the expression of Ux there, which is x squared plus 3x plus 2, then minus 1. And simplify to 1 over x squared plus 3x plus 1. And then W of U of negative 3 is 1 over 9 minus 9 plus 1, which is 1, right?
Yeah.
Okay, so this is all about topic 4.